Alright, today we're going to talk about water, its properties, and the creation and breakdown of polymers. First, let's start talking about water. Water is a molecule. If you remember, a molecule is created by two atoms that are nonmetals, and both oxygen and hydrogen are nonmetals. Even though hydrogen's on the left side of that periodic table, it's floating above, and I said that was that one exception to the rule of to the left and to the right of the zigzag line. When we look at oxygen and hydrogen interacting, we got H2, that's the two H's, and the O for oxygen. That has the interaction to put 8 electrons in that outer shell of the water molecule right there. You got 2 electrons in the inner shell with oxygen. Oxygen normally has 6. Each hydrogen provides 1 more electron, so that there's 8 electrons total. Now, when you look at this picture right here, you'll notice this little negative sign and this positive sign. If you remember before, we talked about electronegativity. We said electronegativity increases as you move to the right and towards the top of the periodic table. Well, oxygen is way over on the right side of the table while hydrogen is way on the left side, meaning oxygen is a lot more electronegative, and that basically tells us that the electrons are going to hang out more on this oxygen side, giving it more of a negative charge, and there's going to be fewer electrons hanging out on this hydrogen side, which is going to give it more of a positive charge. So that sort of lends itself to some of the big properties of water, which we're going to sort of go into in a second. And that first property of water that's super important is created by that electronegativity is the polarity of water. And we just sort of talked about that. Oxygen is much more electronegative, so the electrons are going to hang out on that side much more often. Because of this polarity that we create, this positive and this negative pole, or these positive and negative ends of water, that allows water to do something called hydrogen bonding. Hydrogen bonds aren't true bonds. They're more attractions that are between two molecules because of the positive and the negative poles, and that holds those water molecules kind of together and gives it an attraction between the water molecules. Really important because water has all kinds of different forms. It can be a solid, it can be a liquid, it can be a gas pretty easily on the scale, and those hydrogen bonds sort of keep water doing its thing, lend itself really big to the properties of water. Hydrogen bonds aren't the easiest things to break, but they do break at times. They're not the hardest things to break either. So it allows water to be a very versatile molecule, especially when a lot of water molecules are interacting. And this polarity and hydrogen bonding are sort of the first kind of basis of everything else that's going to be happening with water. Water has what's called a high specific heat capacity. That basically means it takes energy to get it hotter, it takes energy to get it colder. If you've ever made a custard in the oven, usually when you put a custard or a creme brulee is something I like to make, you put the stuff inside a little ramekin, put that inside a big pan, and put water around it because water acts as an insulator because of that high specific heat capacity. Well, high specific heat capacity in biology is really important because it allows things to sort of maintain temperature. We don't really have to worry about our temperature fluctuating too much because our bodies are pretty much all water, and it sort of maintains that stable temperature for us around 37 Celsius or 98.6 Fahrenheit. Hopefully we start getting into the metrics, so you should be knowing that our body temperature is right around 37 Celsius, just in case you weren't familiar with that. This is important for organisms for maintenance of temperature, and think about land masses. Dirt and soil gives away heat and takes in heat a lot faster than water does. So when you look at a place like Nebraska, it's got really hot summers, really cold winters. It's landlocked in the middle of the country. There isn't a ton of water other than some small rivers and lakes there, and that's about it. So I mean, you have big temperature swings between the seasons. Whereas if you go to Portland, which is over on the west coast up in Oregon, even though it's way higher on the country, closer to the pole, it still maintains a much more consistent temperature throughout the year because it's got that big Pacific Ocean that's sort of maintaining that temperature. So that high specific heat capacity helps us both in the ecological sense, where it's maintaining temperatures and climates, and also in the individual organism sense and maintaining our internal temperature and helping keep us at a stable place. Cohesion and adhesion are put together. They're kind of the same thing, kind of different. With cohesion, co means together, you stick to yourself. Water molecules tend to stay together. If you see this picture over here, we got these little droplets of water, and they don't just fall off or repel from each other because these water molecules have a lot of cohesion because of that polarity and the hydrogen bonding that occurs between the molecules. Adhesion, this means that water molecules stick to everything. So right here we're actually seeing a little bit of both, because this water drop is sticking to the pine needle that's probably got some polar stuff on the outside. And when we talk about cell membranes, you're going to know that there's some polar stuff on the outside of this living tissue right here. And I mean, think about when you get out of the shower. When you get out of the shower or the bathtub, you have to towel yourself off because the water sticks to you. If you don't, it just stays there. So that's kind of the cohesion and adhesion working together, and that's all because of that polarity of the water molecule. Another thing that happens because of this cohesion and that polarity is something called surface tension. Surface tension allows water to sort of stick to things, and it creates a sort of skin on the surface of water. If you've ever looked at your cup of water, there aren't really holes. Like if you swirl your water, it sort of stays together on the top. It sort of makes a nice flat layer. If you look at a picture of the ocean, the water's nice and flat. You don't have these big plunging holes. That's because the surface tension is created. It allows things to float on top of water. Some organisms can actually walk across water, and this just sort of makes water one of those essential molecules that sort of makes life possible. And kind of the combination of all of these things leads to other things that can happen. Capillary reaction, where if you stick a piece of paper inside of water, the water will climb up the paper. It's all this combination of the polarity, the adhesion, the cohesion, surface tension, and the high heat capacity of water. A lot of things. If you want to learn a little bit more about water, check out this website. This is where I got some of the information you saw here, but there's a lot of other stuff. I could do an hour just on water properties, but we're going to move on a little bit. Now, molecules interact with each other. We were talking about water sticking onto things and having that adhesive property. Well, when molecules interact with each other, usually like things like to interact with each other. Polar molecules will interact with polar molecules. Nonpolar will interact with nonpolar. A little different than chemistry. We always say the positives and the negatives go together. When we're talking about molecules, polar molecules are always going to stay with the polar ones, nonpolar with nonpolar. Since water is a polar molecule, something that we say is hydrophilic, that word literally means water and loving. Hydrophilic are going to be polar molecules. These are molecules that really interact with water because they're polar, just like water is. So water can easily attach to those molecules. It can break certain things down. If you've ever put salt inside of water, you know the salt dissolves into it. That's because salt is a polar molecule as well, or a polar compound, I should say, and it'll dissolve into the water. Hydrophobic things are items that happen to be nonpolar on the outside. Nonpolar or hydrophobic, water hating, are going to not interact with water and create some kind of separation. You've probably seen this at some point if you've ever poured some oil and water into the same cup. We see that these two things don't interact at all. Well, what does that tell you about the oil? Do you think it's polar or do you think it's nonpolar if it's not interacting with the water? Hopefully you're figuring out by now this is going to be a nonpolar substance that's sitting on top, and water happens to be the polar substance on bottom. So these interactions are really important as we move forward in AP Bio. One thing I always tell kids is that AP Bio is kind of like the combination of biology and chemistry. We sort of really put it together because we're trying to figure out what the why and the how the things actually work. You guys learned a little bit in Bio 1 about what's happening. Here we're going to learn the why and the how, and that always goes down to the chemistry of it, because chemistry is kind of the fundamentals of life. Now, one thing that we're going to practice in class is with functional groups. Functional groups are sets of atoms inside a molecule that sort of tell it what they do. When we talk about proteins, this kind of becomes really important, but every organic molecule is going to have some kind of functional group somewhere. You're going to have a chart, you're going to draw these, we're going to create these with the molecule sets in the classroom. So yeah, you should be able to recognize these. We'll get to that later, don't worry. And that's something we're actually going to do in class tomorrow. But this is something that you should sort of familiarize yourself with and learn the names, because if you understand the functional groups, you can possibly identify what kind of molecule it is or what the molecule is going to do, because the functional groups will sort of tell you how it's going to behave. So it's almost like a cheat sheet, similar to that prefix and suffix page I posted on Classroom for you guys that sort of helps you break down words. The functional groups help you break down what molecules actually do with each other. Now, let's talk about you. What's making up you? Well, this segment right here is what's making up you. Look at what makes up the big chunk. About 2/3 of you is straight up water. Water inside your cells, water around cells, water that you take in, all of that is just sort of helping to maintain your temperature and do all the properties and allow for things to dissolve inside of you and be transported inside of you. We got some ions right here, but this is an important one. Macromolecules, and this is what we're going to focus on next. Here is the macromolecules. Of this little chunk that makes up a little bit more than 1/4 of you, here's how the macromolecules break down. Look at this. Protein. Lots of protein inside of you. That's pretty much what makes up you and what you do. Anytime people ask me, what do proteins do? I pretty much say everything. Proteins pretty much do everything for you. They help you move, they help protect you, and we'll do a whole nother one of these videos just on proteins, and one on nucleic acids, one on carbohydrates, one on lipids. But proteins do a lot of stuff for your body. Nucleic acids, that's your DNA and your RNA. We'll get to this stuff later. Carbohydrates help with some of the structure and help with energy, and lipids. I might have more lipids than I need, but that's okay. Yeah, lipids make up an important role, and they play an important role. These 4 things are your 4 macromolecules, and that is something you absolutely need to know, because that's pretty much the heart of this class. How do these macromolecules make up you, and how do you work? The nice thing about biology is that if you understand how one cell works, you understand how all cells work. If you understand how one organism does things, you sort of can have an idea of how all organisms do things, and that's because we all have these same building blocks, these proteins, these nucleic acids, these carbohydrates, and these lipids. So that's one of the big things in bio, and we'll get to cell theory when we start talking about cells, but if you know how one of us works, you know how pretty much everything works, and you can take it from there. So when we talk about macromolecules, macro meaning big and molecules, then we have to understand what their monomers are. Monomers are the individual units that make up macromolecules. Macromolecules are going to be a chain. They're going to be a chain of individual single units, and that single unit, or monomer, mono meaning one, is going to be the single unit. You should know that what each one of these is. By the way, in my world, CHO is carbohydrate. That's just something you'll get used to. We'll talk about in class, but every carbohydrate is made up of carbon, hydrogen, oxygen, so I just call them CHOs. It's quicker and easier to write. The monomer for a carbohydrate is a monosaccharide. The monomer for a lipid is kind of weird because it's kind of a combination of a few things, but every lipid has a monomer of fatty acids and a glycerol molecule. Every monomer for a nucleic acid, either DNA or RNA, is going to be called a nucleotide, is that individual unit, and the monomer for every protein is going to be an amino acid. Now, different combinations of amino acids make different proteins. Nucleotides are in different orders in different parts of your cells. There's more or less fatty acids and glycerols attached to each other and different things, and different combinations of monosaccharides make up different carbohydrates. We'll get to that later, but what you should know from here, absolutely, you should know the macromolecule on the left here and the monomers that make up that macromolecule on the right-hand side here. The process of linking monomers to make a macromolecule is called polymerization, because a polymer is many monomers, poly meaning many. So polymerization is the process of putting those polymers together. And when we go through polymerization or make a bigger chain of things, that happens during a process called condensation. When condensation happens, a molecule of water is removed from the equation. The next slide, I believe, we're going to see a picture of what happens with polymerization. When we break polymers down, because one thing you learn about our bodies and every organism is something's going to get put together at some point, it's going to be broken down at another point. So when we break them down, that happens through hydrolysis. Hydrolysis, hydro meaning water, lyse meaning to break. So literally, water is used to break the bonds of the polymer. So let's look at a picture of this. We have condensation right here. You'll notice we have one monomer right here. We have another monomer right here. That OH right there is a functional group. That OH is a functional group. And look at this, OHH. What happens if I put those two things together? Guess what? That's going to combine and form H2O. As H2O is pulled out, these two chains of the monomer get hooked together. So I lost a water and I created a chain. Look what happens. That OH is right there. It's going to join with another monomer. Water comes out. I just had a condensation reaction. Water molecules were taken out to create a longer chain. And we said the opposite of that was hydrolysis. We put a water molecule in, and that bond's going to get broken. Now we got this one went right down here. These two guys still hooked together over here. Add another water molecule in, bam, and bam. In your body, we have these constant cycles going from place to place. And that's something that you're going to see. When we make energy, we break energy. We break energy down. When we make a polymer, we're going to break it down into monomers. And that's something you're going to see constantly throughout this class. So just sort of get used to that. If something happens one way, it's going to go backwards to get back to where it started, because our body's just a big recycling bin. I'm going to stop right there right now. And when we get to class, we'll talk about functional groups and talk about this condensation hydrolysis again. Thanks.